Prova. Okay, I'm restarting the recording. So, good afternoon, everyone. Today we will do an in-class practice on the topic of information retrieval. We will talk about search engines, and we will have a look on how we can use information retrieval techniques to retrieve documents. So the lesson of today, we start with a brief introduction to information retrieval. Then we will pass through web search engines. So we'll discuss how we can search for documents on the web. And so we will discuss some of the algorithms that are not necessarily related to natural language processing, but they are the main foundations for search engines on the web. So hits and PageRank above all. Then we will just introduce Elasticsearch, that is software that we can use to build a search engine that is actually used in many occasions. And we will see how we can integrate natural language processing ideas into this search engine. So without further ado, let's start with, information retrieval. So the idea of information retrieval is that we want to find some material. So here we want to find some material of a structured nature, because we are dealing with text actually that is unstructured. It's not like tables that are structured with attributes and data. And we want to search within a large collection of data, so a large collection of textual documents. So our idea is that the material we want to find are some documents that in the web can be web pages, and in our context can be textual documents. The document we are searching for are composed of structured data. In this case, is text. In our case, in the majority of cases, when we refer to information retrieval, we think about it as information as text. And finally, we want to search for documents that are in large collections of data, so large collection of documents. Imagine the web pages that exist in the world. They are very large collections of data. They're usually stored in computers, on servers. So here there is the idea. When a user comes, provide a query, and this query is used to search for documents. What we want to do as an output of this process is a ranked list of documents, and this ranking is reflecting the answer for the query given by the user. So we have a query that is the input of our system. In our system, we have this collection of documents that are indexed, that we know what is in this part. And what we want to do is to provide a list of ranked documents, such that the first document in the list, in the golden case, is able to answer the query inserted by the user. So this is the retrieval part of information retrieval. So the simplest model that we can build for a search engine is a model based on a set theory. It means that we can consider a document as a set of words, so a set of elements inside the document. In this case, there are words. And we can define queries as Boolean expressions. So the user can insert a query, and it means that it can define, like, I want a document that contains these words and does not contain other words. Actually, this is what is used in most of the commercial systems. When you are in an e-commerce website that is not Amazon, because Amazon is actually a tech giant also, but if you are in a traditional commercial, like e-commerce system, you will find something like this. So you will find something that when you enter a query, decompose it into words, and then use some sort of binary matching between words that you inserted and the words that are in the documents. And so then it's able to give you the documents that satisfy your query. The idea is that each time we run these kind of models, we need to process our text, both the query and the documents. So the idea is that we will have some word tokenization technique that decompose our document into words. Then we apply some lower casing. It means that all the words and all the text in the documents and in the query are lowercase. So everything is in lowercase. And then we can actually also use some kind of advanced processing techniques, such as stop words removal, that we can remove both from the query and from the documents. And we can apply lemmatization or stemming. It means that each word in the document can be converted into its root form. So it means that if we have a document, we apply this processing technique. And at the end, what we have is a list of words. Actually, here, this is not the processed list, because this should be lowercase. But however, okay, a little bit of delay with the pen, but yeah, it means that these are the words that compose our documents, and so we can use it to index the documents and to then look up for searching documents. So I want to make a distinction here between the information need and the query. So the query is the thing that, like, the input of the system, of an information retrieval system. And it's actually what the user type on the keyboard or like speak on the microphone to search with the voice. But this is what the user inserts in the search engine. We can distinguish the query from the information need. Here I have an example. So the query for a user, that is like the information need for the user, is that you want to know if tomorrow is sunny in Turin. Tomorrow morning is sunny in Turin. What it types on the keyboard is different from its thought. So the idea is that it inserts some words that represent the information need, but they are not actually the real information need. Because if I would like to know if it's sunny tomorrow morning in Turin, I perhaps will enter weather tomorrow Turin. So some keywords that represents my information need. And this is something that we need to think about. So what we do once we have our collection of documents and our collection of and the queries. So if we have our collection of documents, what we want to do is to pre-process them and do an indexing part. It means that we can build an index. So it's a structure, a data structure that stores all the information we need at query time. It means that we don't need to do the text processing, lemmatization, stemming, stop word removal, and so on and so forth during the query, because it's very expensive in terms of computation. But we do this at indexing time. So we have the collection of documents, we index them, and then we can use them at query time. We can use this information to have a speed up on the search process. So here I have an example. We have different documents. So here, in this case, I put as examples the terms that can be part of the in-class practice number 1, 2, and 3. So the first one has some keywords, some words that are like Python, NLP, tool, process, model, natural language, deep learning framework, so on and so forth. The second one, of course, has both natural language, because it's the main topic of all the in-class practices, but it also has like vector, process, embeddings, word2vec, and so on and so forth. In the in-class practice 3, we talk about sentence embeddings. So instead of having only word2vec, gensim, and so on, we also have sentence embeddings, word2vec, sentence2vec, vector, because it's shared with the first one, We have Gensim, this is shared in the first one, but it has some differences. So the first thing we need to do in this case is to create a dictionary. It means that we need to collect all the unique words that are in all the documents. In this case, there are 3 documents. We need to collect all these documents and all these words, and create a dictionary. It means that this is the process of mapping a word to its an ID, so an ID that represents the words. So doing this, we can obtain this kind of structure. So for each document, we can have a list of IDs that represents the IDs of the words that are in the document. So here you can see that if I see like Python, natural language are shared among all the 3 documents, and I have Python, 6 and 7 that are like here, natural language. So you can see that you have the list of words, and of course the same word is mapped to the same ID across all the documents. So this is to create our index that is able to speed up the process of retrieval during the query time. So when the user insert the query, we can just look up and we have all the documents already processed. Okay, so the dictionary contains all the terms that are in the documents, and we have a set of unique words that are in our corpus. In this case, the corpus is the list of documents we want to index. Sorry, I will just close the door. Okay, I think it's a little bit better, less noise. Okay, so so we have for each term, we can think about each term linked with a list of documents in which the term occurs. So instead of having this kind of representation where we have the document and then the list of words that belongs to that document, we can actually have the opposite. So for each term, we have a list of records, so in this case, documents, so which documents the term occurs in. So in this case, each item in the list is called posting. And so we have a posting list that contains this kind of information. This is actually useful because if you think about it, when a user inserts a query, it inserts a list of words. And so if we have for each word the list of documents that contains that word, we actually can do some sets of like intersection and union operations over the set of documents, and we can retrieve the documents that answer the query by the user. So this is called inverted index. And so when we create, so a retrieval time, sorry, not a retrieval time, at indexing time, when we want to index our corpus, what we do is to have several documents. For each document, we apply our processing techniques. So we remove stop words and so on and so forth. And instead of creating a structure that contains document and the list of words contained in the document, we can create the inverted index. It means that we have for each word the list of documents that contain that word. So this inverted index is very useful because if I then search for, I don't know, sky and wind, what I can do is to retrieve actually those 2 words in the list of terms that I have, and then I can look up for documents that contains both sky and document. So I can give to the user the document number 2 because it contains both sky and wind. Is it clear? Is it clear why is it useful? If you have a question, please raise your hand. I'll try to answer. So this is like those techniques are the basics for traditional information retrieval. So traditional means that something that was born like when text processing was the core of information retrieval techniques. So we have not so much natural language processing in this case. We have just a few techniques to remove stop words that can produce noise. We can have lemming and stemming to have a more comprehensive list of terms, because actually if we don't have like watching in our corpus, but we have watch, we can actually retrieve some documents. So what are the limitations of traditional information retrieval? Well, actually, the standard, so traditional information retrieval use syntax of both the query and the document to compute a relevance score. So if you imagine the example we have here on the slide, I have Alice goes from her office to her home. So this is a sentence. And we have another sentence that is Alice goes from her home to her office. So we have the exact same set of words, right? Because we have Alice goes from her office to home. We have those words that are actually the same in both cases, but in our understanding, if we read those questions, those sentences, we have a perfect match in terms of syntax, but they are semantically different, because in one case, Alice goes from her office to home. In the second case, Alice goes from home to the office. So it's a semantically different meaning. Even if the syntax is like, if you consider our model, so the model that considers documents as a set of words, we have a perfect match, because the document is actually containing the same exact set of words. So what we should consider, we should think about it, is the fact that we have that the semantic information, when we consider this kind of model, is lost, because we don't consider the order of words, and so we cannot actually derive a real semantic meaning from the sentence. So we should pay attention to this part of to this thing. And if we want to build a search engine that also considers the semantics of the sentence, we should add something more. So what we can add, so we can use neural information retrieval that actually use neural models, so neural networks. We have seen with Professor Cagliero transformer models. We have seen together sentence to vec, doc to vec. We have seen word to vec, and so on. We can use these kind of models that are able to encode some semantic of the words to create a semantic search engine. It means it's a search engine that also considers the semantic of the sentence. So in the exact same case that we had in the previous slide, so we have two sentences. Alice goes from her office to her home, and the other one is Alice goes from her home to her office. We have actually two different representations from the sentence. So we don't have the exact same representation that we had before. We have two different representations. And in this case, we can actually create a vector space model that is actually a vector space that contains the representation of the sentences, such that we can then compute the similarity between those vectors to compute the relevance between the two. So if in this case we have two separate sentences, but if we have a set of documents, we can embed them in this vector space, and then we can embed the query to actually retrieve the most similar documents nearby. So if we have multiple documents, we have multiple of these vectors. And what we can do is to actually encode also the query using the same process, and then compute the nearest neighbors to have the set of documents that answer the query indexed by the inserted by the user. So here, a little bit of the differences between the two. We have sparse or traditional vector representations that we had before that has actually the list for each document. So this is a document B1. We have the list of terms that are contained in the document. So we have one if the list, like the ID 0, 1, 2, etc. So if the word 0 is contained in the document, we have a 1. The word 1, 2 are not contained, so we have zeros. And so this is the representation. How big is this representation? So what is the length of this vector is actually the length of the entire vocabulary. Because for each word in the vocabulary, we should store the information of whether the word is present or not present. So we can have like dimensions that can exceed even 50,000 elements. Instead, what we want to do is to create a dense vector representation, similarly to what we had with word2vec or sentence2vec and so on. So we want a dense vector representation that contains the information on like abstract information that we cannot interpret. So it's not like this word is contained, this word is not contained, but it's actually a condensed version of the information that we can then represent in a vector space and compute all the operations that we have already seen. So the first thing we can do is to actually think about, okay, I can use word2vec to compute the semantic vectors for my documents. Yes, I can. It's not an optimal solution because I want a vector that represents the entire document. So I don't want a vector for each word. I want a vector for the entire document. So I can then compute the average of all the words contained in the document to compute the final vector representation for the document. But it's actually not optimal because we have seen that word2vec is more is designed to embed vectors of words and not for entire documents or longer paragraphs and so on. So what is better is to use like transformer models. So we can use these deep encoder models. So transformer-based architectures to encode and to compute semantic vectors for the entire sentence or for the entire document. And then we can compute the cosine similarity between those vector representations to see whether two documents are similar and if they are similar with the query. So we can use those information to encode. You can use these architectures to encode both the documents and the query. But however, those transformer models are not intended for this specific purpose. They are pre-trained on a large set of documents, yes. But what is state of the art right now is to use these kind of architectures. So we have two instances of the same model. So we have BERT or other transformer models. We have two sentences or two documents that enters both to the first instance or the second one. So we have those two sentences that goes into. Then we have a pooling layer because, of course, BERT does not produce a sentence embedding. BERT produces a word vector representation for each token that we have in the vocabulary, in the sentence. So we have different vectors, one for each token in the sentence. What we want to do in this case is to aggregate all these vectors. So we take all these token representations. We can do a pooling stage where we can do actually different things. We can take a specific token, that is the CLS token, or we can actually do the average pooling to have the average of all the tokens. And so we have a vector representation for each sentence that we have in the input. So sentence A, we have U as a representation. Sentence B, we have V as representation. And what we want to do is actually, if we have pairs of similar sentences and different sentences, we can actually compute the cosine similarity and use them as use this as a loss to backpropagate to the architecture, such that we can train a model to explicitly create semantic meaningful representation for the entire sentence. So the idea is that we use the same architecture here. So we use transformer models, but we design the architecture on top of BERT or in top of transformer models such that it is specifically trained to generate semantically meaningful representations for the word. So in this case, we have like the architecture is composed of a larger encoder model that can be BERT. We can then have an aggregation layer that pass from a sequence of vectors, one for each token, pass to a single vector representation for the entire sentence. For this, we can use the CLS token, like a specific token that is trained to be representative of the entire sentence, or we can use the average pooling. So we can use a function that create the vector representation for the sentence by using the average pooling. And then at the end of this process, we have a sentence representation both for sentence A and sentence B. And if we have a lot of training examples, we can define a training loss by using the cosine similarity of the two sentences. And if we actually have those information, we can backpropagate and we can run the training procedure to train these encoder models to produce semantically meaningful vector representation. Okay. Yes, this vector representation is used for indexing and retrieval. Yes. Per token, yeah. Yes. So we have the sentence that we have BERT here. If we have the cat set on the mat by actually we have if you consider like word tokenization, like don't mess up with tokens and things, but if you consider word tokenization, we have this kind of splitting, and what we have is actually at the end, at the output of BERT, we have a vector representation for D, we have a vector representation for cat set on the mat. So we have 6 tokens, or 6 vector representation, one for each token. In this case, a token is a word, but you can generalize this. And actually, the pooling stage is actually can do 2 things. We can do average pooling, and so we do the point-wise average over all the vectors and create a single vector representation. Or we can think about we will see this kind of thing also in the next in-class practice. This is just introduction to let you know how neural information retrieval works, but we can actually also have a specific token before the sentence. That is the CLS token that is represented by a separate token. And if we inserted this, we can discard all this and use this vector only. During training, if we use this vector representation, during training, the model adapts to store all the information that it needs for the semantic representation of the sentence in this single token. So this is a specific token that is inserted to be the representative of the entire sentence. So we will see this in the like next week when we discuss, like we have a longer in-class practice on transformers, attention, and text how we can address the text classification task with the transformers. And both of those are techniques to encode the meaning of a document or a sentence in a single vector representation, because by default, this is not done by BERT. So BERT is not a model to create sentence representation. It can be a model to create sentence representations, but by default, it produces a single vector, one for each token, for each word in this case. Is this clear? Okay. So once we have our model, we have a model that is based on transformers, sentence to vec. We can also use sentence to vec to encode the information of the sentence. Whatever, we can have a model. We can even have a Boolean model, so we can just run like matching between words and so on. How can we evaluate it? So the idea is that what we want to do is to evaluate the efficiency, not the efficiency, but the performance of our search engine. And to do so, we need a set of queries and a set of documents. For each query, we should define a set of documents that actually answer to the query, so that are relevant, documents that are relevant to the query that has been inserted by the user. So for each query, yes, we have a set of relevant documents that answer the query. So we have a data collection that we can index. We can create the index for our model, for our corpus. We have the model, and then we have a set of queries and documents that answer the query. So in this case, we can use these informations to compute some metrics such as precision and recall, to then evaluate our model and say, okay, this model has this this score for precision, this score for recall, and actually, how can we define this precision and this recall? So we have you have in mind that we have a corpus like of 1 million documents. Then we have one query and like 5 documents in the corpus that answer the query. So we can compute the precision as the fraction of the results that have been returned by the model that are relevant to the information need. So we have the query, like the query we can, in this case, consider the information need, the passage from the query to the information need is done by the model. So the model should be able to generalize the query inserted by the user to capture its information need. So we have a query, we have our system. The system answers us with a set of ranked documents. And we can, so those documents are relevant for the query, for the model. Then we have a set of, I can change color, yes. Then we have a set of relevant documents. And we can actually compare those two to compute precision. So the precision is a fraction of returned results that are actually relevant to information needs. So a subset of this can be relevant, so perhaps 2 of them. And we can divide this by the total number of documents that are relevant. So in this case, 2 out of 3. So in this case, the precision would be 2/3. And no, sorry. Yeah, the 2/3 in both cases. But here, the denominator, we have the set of documents returned by the model. So sorry. In this case, I can actually, this is okay. If I have 4 documents returned by the user, by the model, sorry, and I have 3 documents that are actually relevant, what I have, as a precision is the 2 documents that are actually relevant, so 2, out of the number of documents that are considered relevant for the model, so 2 out of 4, so 2, so it's one off. Okay, the recall is as the same numerator, so we have the number of documents that are relevant in the results given by the system, divided by actually the number of total documents that are relevant. So in this case, we have the recall of, like, we have 2, this is the same numerator, but the denominator, we have this. We have the total number of documents that we can have as relevant. So we have a recall of 2/3. And in this case, those are some of the metrics that we can use to evaluate our information retrieval system. Is this clear for you? How we can compute this precision recall? We have also other metrics, but actually those 2 are very important, and I want to mention you, and I want to be sure that you understood. Is it clear? Okay. Okay. So if everything is clear, that's all for the introduction to this information retrieval world. We can then pass to the search engines, but on the web. So one thing that we consider in our information retrieval system is the query. We have our model that is able to look up to search for documents that are relevant to the query. But on the web, we don't actually have only like the user insert a query and we have our system. In this case, the collection of documents on the web is not just a list of documents. The list of web pages is not just a list of web pages. Is a list of documents that are actually linked one each other, because we have hyperlinks. We have links, like in the web page, we have the link that we can click to follow the link. And so those, the web pages are not like just a list of documents, but they are connected one each other using some links. So we have, we have a definition of a hyperlink that is a link from a web page to another. And so actually what we have is not a list, but we have a graph of documents interconnected one each other. Okay, the thing that is very relevant when passing from search engines to web search engines is the fact that we have this kind of structure. This is a graph structure, and we want to perform some kind of link analysis on this on this data structure to have some ideas on not only if web pages, if some web pages answer to my query, but also if they are actually relevant overall. We want to know if they are authoritative, if we can trust those web pages, and so we can perform link analysis to actually encode also this information in our ranking. So if we have a score that is able to give us the information if whether a web page answer to a given query, we can also use a score like the score we discussed that are based on the link analysis to boost some of the web pages that actually are more authoritative than others. This problem was actually a real problem in early 2000, but it's actually the idea of using link analysis is used like everywhere, like in different fields, even in summarization or other fields. We can use this link analysis when we have graphs and we want to compute the importance of some nodes in the graph. So the idea is that we have the hyperlinks that go from one node in the graph to another. So here I have like my web page A, and I have a link like Polito University website that links. Yes, it's already there. The arrow. So I have a link that goes from this web page, so web page A, to the web page B, that in this case is www.polito.it. So these are the kind of structure that I have. In this case, if I just have this information, what website is more important, A or B? Actually, B. Who said B? Yeah, it's actually B. Yes, it depends on how you define the importance. But actually, B can be a correct answer, because if a web page is referenced by another, it means that the A web page, the A web page is actually giving credit to B. So it's giving like importance to B, because if I reference them, it means that there is something that is reported in B that is relevant to what I'm saying in page A. So yes, I want to introduce you today two algorithms for link analysis. One is ITS, the other one is PageRank. I don't know if anyone is familiar with one of these link analysis algorithm. Both of them have been created for the web, and the idea is to associate to a web page a score or multiple scores that give us an idea of the importance of the page in the graph, like in the web. So HITS is an algorithm that has been implemented by John Greenberg. The idea is that we have two different kind of pages. We have certain pages that contains a lot of links, outgoing links, so from the page to other web pages. And in this case, they are called hub because we have, we have hubs because they contain a lot of links for, like, they serve as a directory of a container of links to other pages. And then we have authorities that are actually referenced by a lot of web pages. So we can do this kind of distinction. We have hubs that contains a lot of outgoing links. Like, this is the intuition. And then we have authorities that contains a lot of incoming links. So we can define two types of scores, one for hubs and one for hubs and one for authorities. So the algorithm assigns two scores, of course. The authority score estimates the value of the content of the page. Instead, the hub estimates the value of the links that it contains to other pages. So if I contain links to authoritative pages, I am a more important hub. So this is the intuition behind. So in this case, yes, D. So in the first graph, so here D has a high authority score because it's referenced by many pages. So it contains some information that is referenced by many web pages. Instead, in the second case, 1 is actually a good hub because it references a lot of other pages. So it contains references to a lot of other pages. So this is the difference between hub and the authorities. So how it works? So the idea is that when we have, we can start from a root set that is in this case is a set of nodes in the graph. These nodes can be actually the nodes that answers the query inserted by the user. For this reason, HITS is actually an algorithm that is run like real time. When you insert the query, you first define the root set, you do all the algorithm, so it's computed each time you insert a query to the document, to the search engine. So the first thing to do is to define a root set. So it's a set of nodes that answers to a query, can be. So it can be created in different ways, so using text similarity and so on and so forth. So we define this root set, and we augment this root set by creating a connected graph from the base set, from the root set. So we interconnect B and D in this case. Sorry. Okay. So we have B and D. We define the base set as the set of nodes that are connecting B and D. So we create this base set by augmenting the root set. And so we have, like, the base set, we have all the web pages that are linked from and some of the pages that link to it. So we define some ingoing pages and some outgoing pages from the root set to define this base set and have this focused subgraph. So this focused subgraph is actually the data structure that we use to compute our HITS score. So we compute the HITS by only on this focused subgraph, so not on the entire web, just because it's like impossible also to define this kind of algorithm at query time on the entire web. So this is the reason why we use this focused subgraph. So we have this subset of the entire graph, And the reason that why we want to construct this base set by including both ingoing, like outgoing and incoming links, because we want to actually define those two information, the information about the authoritativeness of a node and the hubness of a node. Actually, the algorithm is not so difficult. It's very simple. It's an iterative algorithm that performs two steps. The first one is the authority update, and we update the authority score of each node using a formula. In this case, we have the sum of the hub scores of each node that points to it. So we sum all the hub scores of each each node that points to a given web page. It's actually will be clearer in the next slides. And then we have the hub update. So we first update the authority score and then the hub score. The hub score in this case is defined like for each node we define we update the hub score by summing up the authority scores of each node that points to it. So we will see that in the first case, the authority of a node is given by the hub score of the nodes that points to it. So if I'm pointed by like important hubs, I am more authoritative. And in the second case, if I am an hub and I point to very authoritative nodes, my hub score will increase. So this is actually, yes, we can see this in a formulation. So here we have like for the initialization, we have all the nodes in the hub, like both for hubs and authority. Those scores are initialized to 1. So for all the nodes in the base set, we have an additional normalization step. This normalization step, like after each update, we normalize the score pay attention to this, because we normalize by according to the sum of all scores. So this is the formulation for authority. So the authority of a node I is given by the authority of the node summed up, like divided by the sum of all the authority scores. Not the number of nodes, not the number of links, but the sum of the authority score of all the nodes in the graph. The same for the hub. We have this normalization summing up all the nodes, all the hub scores for all the nodes in the base set. Okay, so we have a simple example here. We have the iteration 0. We initialize everything with 1. So we have 1 for each, for both for the hub score and for the authority score for all the nodes. Here I'm representing the graph for which we want to compute the hub and the authority scores. Iteration 1A, I update the authority of each node. So this is fixed. This is the same of the first one, right? So this is the same. Oh, sorry, not this one, but this one. So this is the same. What changes is this second part. So I want to actually compute the authority for the node A. So here for the node A, I follow the rules. So each node authority score is set to be equal to the sum of the hub scores of each node that points to it, right? So I have for the node A, what are the nodes that points to it? So I have only B. So in this case, the authority score for A is equal to 1 because it's the sum of the nodes, the hub score for the node that points to A. So I have only B. What happens to this? Okay. So I have only B that points to it. So I actually have the authority score for A that is 1. And if I do this for all the nodes, I have the authority score for all the nodes. So for A, I have 1. For B, I have 0. Why I have 0? Because nobody is pointing to B, right? So if nobody is pointing to B, the authority of B will be 0, because it's the sum of all the hub and so on and so forth. For C, I have 1 node pointing, so this is A. In this case, A is 1, so I have 1. D is A also, so I have 1 even for D. Iteration 1B, sorry, okay, 1H, yeah, the hub update. I update the hub score for each node. So how I set it is equal to the sum of the authority scores of each node that it points to. So the nodes that are referenced by. So in this case, I have if I compute the hub score for A, I have like the sum of the authority scores for both C and D, because I'm pointing to C and D. So I sum the authority score. The authority score for C is 1. The sum of the authority score for D is 1. I sum this, and I have 2. And then I can compute this also for B, C, and D. Why for C and Why for C and D I have 0? Yes, well, because they are not pointing to nobody. So I have 0 score for the hubness of those two nodes. All right, what misses? Normalization. So in this case, I have the sum. Yeah, in both cases, the sum is 0. But I sum up like 1, 1, and 1, and I have the denominator for this part. And if I sum 2 and 0, I have the denominator for this one. So I normalize by summing up the total number of hub scores and the authority score in the case of normalization for the authority. Is it clear? Is it clear how the process? So if I iterate this process multiple times, I will arrive at a convergence. And in this case, I will have the hub and the authority score for each node. So if you see, you have for each node, so for D in this case, but for any other node, I have an authority score and an hub score. So in this case, I can go on and I have 2 scores. This is the code that we can use to actually compute this information, like the hub and the authority scores, by using its in NetworkX. That is like a library that is used to define and run some algorithms on graphs. And so in this case, I just use import NetworkX. I define a new graph. What can I use? Yeah. I define a new graph. I had some nodes. So in this case, I have A, B, C, and D. So these ones. I had some edges. So from A to D, from A to C. So I'm following this kind of structure, right? And from B to A. So I define this. And then I run the algorithm by just running it over my graph. It's actually very easy. If you do this, you will see that, of course, A will have a high hub score because it references more pages. And instead, C and D will have a higher authority score because they are actually referenced by a big hub. Big in this case. We have just 4 nodes, but it's actually the idea that matters. Yes, you will also find this example, like the code, if you want to copy paste this on the GitHub of the course, and you will actually have 2 examples, one for this and one for PageRank. Is this clear for you? Is it clear how it works? Okay. So the main problem of it is the fact that we are defining 2 scores. So which is the score that we need to consider when boosting a page? The authority of the hubness score, perhaps the authority score. But the real problem of ITS is the fact that we need to compute this algorithm each time the user inserts a query. And this is a problem because we don't want to compute something real time when the user inserts the query because we want to return faster the results. We want a fast algorithm that is able to, a fast model, a fast search engine that is able to answer the query from the user. So this is why in 1996, two guys, Larry Page and Sergey Brin, that are actually the founders of Google, created PageRank. PageRank is actually the secret sauce behind Google. And the idea is that they want to define a score that can be computed offline. It means that if I have a collection of documents, I can run this algorithm, and a collection not of documents, but a collection of linked documents. So if I have a graph, I can compute a score in actually offline, so without having the need for the query by the user. That gives me an idea of how important these nodes in the graph. So, like its page is an iterative algorithm. It means that it iterates multiple times till convergence. Its is query dependent. Its is query dependent. So it means that the scores are influenced by the search terms, and it's executed at query time, and it computes the two scores, so all the things that I already said. And instead of the PageRank is run on the entire graph, instead it is computed on a small subset of documents that are actually relevant to the query, but I actually need the query to define them. So these are the differences. PageRank is not query dependent. It's not executed at query time. It computes one single score, and it is computed on the entire graph of the web in this case, but we can define different type of graphs. I know it's okay. So the idea of PageRank is that I am a random walker that like I'm running over the graph. The idea is that PageRank give us the probability that if I randomly walk over web pages, I will end up visiting a specific page. So for this specific page, I have the probability of being here if I perform a random walk over the graph. So yes, the idea is that a person is randomly clicking on links, and what is the probability that it will arrive at a particular page? So we have different rules in PageRank to run PageRank. Rule number one is that links from one page to itself, so self-citations, self-links, are ignored. So I will not consider these kind of links. Second, if I have multiple links from one page to another, so if I have something like this, I have multiple links from A to C, I will consider them as being a single link. So I compress all this in a single link. Yes, it's not I'm not a good drawer, but yes, the idea is that I compress all these links in a single one. And finally, for the initialization of PageRank, because it's a distribution probability distribution, I want to initialize it as like the sum of PageRank values will be summed up to 1 because it's a distribution, probability distribution. So the initialization in this case, in this specific case, when I have 4 links, it's like for each node, I initialize this as 1 divided by the number of nodes. So in this case, 0.25. And this is the PageRank formula that is actually driving the success of Google since 20 years now. So the idea is that the PageRank for a given node, in this case X, is given by two different terms. The first term, so we have this lambda parameter that weights those two terms. This lambda parameter is called damping factor. And actually, lambda is the probability to follow a link once I am in the page. So I arrived in a web page. What is the probability to follow one of the links in the web page? So not to close the tab or change the address on the web browser. This is the probability of following the link in the web page. Instead, 1 minus alpha, so this one, if you see it, it's like an uniform probability over all the pages. And the idea is that this is a teleportation link, the teleportation factor. It means that I just close the tab, open another tab, and go to another link. So I'm teleporting to another link in the tab, in the web. So we have those two parameters. So this is the probability of going to a random web page. Instead, this one is the probability of visiting one of the pages that are linked in the web page. Actually, lambda is usually set to be like 0.85. It's a hyperparameter. And yes, in this case, I have n, that is the number of total nodes in the graph, and the PageRank score is equally split at the beginning over all the links. And each time I for the computation of this term, each time I'm giving, like, each page is giving is PageRank to all the outgoing links, and I equally split all my PageRank to all the web pages. So this factor here is defined as the sum of, for each outgoing link from Y to X, like in this case, the incoming link, because I'm considering the PageRank of X. For each incoming link, I have the PageRank of Y divided by the number of outgoing links from Y. So the idea is that if I have, this is Y, and if I have three of them, I will equally define, I equally divide the PageRank. In this case, if I have a PageRank of 1, this is not going to happen, but just to be clear, this here divided by out Y, yes, this is the PageRank of Y at the beginning, so it's 1, divided by the number of nodes that are pointed by Y. So in this case, if this is X, the contribution of Y to X is 1/3. Is it clear? I'm computing this? Okay. So let's test how PageRank works. So I have this graph. I have A, B, C, D, and E. Here I have this graph. Here I reported the formula. So let's initialize this. So for the initialization, the score, the PageRank score for each node is given by 1 divided by the number of nodes. So 1 divided by 5. In this case, everything is initialized to be 0.2. Okay, first iteration. Yes, I should compute the number of outcoming links from each single node. So here for A, I have 0 outgoing links. For B, I have 2 outgoing links. For E, I have 1 outgoing link, so on and so forth, because I need it here, right? I need it as a denominator of this formula. And I can actually compute the PageRank over the first iteration. Let's see just one of them for D. So for D, if, yeah, I didn't put this here, but alpha is equal to 0.5, right? I'm just putting this value to have like very easy computation. So I apply the formulation. 1 minus, no, it's not alpha, it's lambda. Okay. So lambda is equal to 0.5. So the first term, okay, the first term is equal to 1 minus alpha, 1 minus, lambda, 1 minus lambda divided by n. So 1 minus 0.5 is 0.5 divided by n. In this case, n is equal to 5. So I have this term that is 0.5 divided by 5, that is 0.1. And then I have lambda, so 0.5, that multiplies the sum of the incoming links. So for each incoming link, I have this formulation to compute. I have just one incoming link for X. So for D, I have the link coming from E. So I have the page rank of E. In this case, was like in the previous iteration, of course, was 0.2. So I compute 0.2 divided by the number of outcoming links from E. So here I have just one outcoming link that goes to D. And so I have 0.2 divided by 1, so 0.2. So I have 0.1 plus 0.5 multiplied by 0.2. In this case, this one is 0.1. So I have 0.1 plus 0.1, and I have 0.2. Is it clear? I'm just applying the formulation here. It's just a matter of substituting numbers to the formula that I have like here at the top. Okay, compute this for C because it's very easy. I have, for C, I have the teleportation probability, 0.5 divided by 5, that is the same for everyone, plus 0.5 that multiplies the number of incoming links, the sum of the number of incoming links, page rank divided by blah, blah, blah. I have no incoming links, so it's 0. And so the page rank is 0.1 because it's computed as the only 0.5 divided by 5. And so on. I can do this like for each node. So for example, for A, I have 0.4. You can see that 0.4 is more than all the others because it's actually referenced by a lot of web pages. I can continue. I can do, yeah, okay. I can continue. I can do other iterations. So one thing to notice here is that if I sum up everything, 0.1, 0.4, 0.1, 1, and 2, so 4, 6, 7, 8, 4, 5, 6, 7, 8, 9, 0.9. The sum of all page ranks is 0.9. It's not 1. So for probability distribution, so it should be 1, right? It's not 1. If I can continue iterating, I will have the sum that is 0.725. So what's happening? I'm just doing bad math. It's actually not. There is something that we should consider once we want to run PageRank over our graph. And the thing is that we should not have sinks. Like we have nodes that actually have only incoming links will become sinks. And this is a problem because there is like a PageRank leakage. And in this case, the PageRank goes into these nodes. And this is actually, because it's defined in this way, the PageRank should not run on graphs that have nodes with only incoming edges. So this is something that we should consider. So everything else in the computation was actually the same. So it's a good example. But in this case, we had a sink, and the sum of the PageRank for all the nodes will decrease each time because we have a leakage of PageRank in this sink. And now we can solve this. Yes. Okay. Yes, sinks can create problem on PageRank. We can actually apply one of two solutions that are mentioned here. We can add an outgoing edges from the sink edge. So if we have a sink node, we can add outgoing edges that goes from the sink to all the other nodes. So this is one way to solve, because if we had one link to all the other pages, it's like having a teleportation to only any of the other pages. And in this case, we will avoid having, we'll distribute actually the page rank that is leaking to all the other nodes in the graph. Yes, the second one is not creating an actual edge, but distribute the page rank of the sink evenly among all the pages. So like a mathematical trick. In the second case, we just add the real link to all the pages. Yes, both solution converge to the same results. The same result. Actually, it's actually the same thing. They are actually doing the same thing. Okay. Yes. The idea is that when we run PageRank, our multiple iterations, it will converge to some values that are actually becoming stable at a certain point, and those are the values of the PageRank, the final values of the PageRank for the given pages. Okay, so if we want to actually run this algorithm over the network X, so the same library I mentioned to you before, we do actually the same exact thing we did before. Of course, we changed the edge configuration because I changed the graph. So we have a link from D to A, from C to A, from B to A, from E to D, and so on and so forth. And I can run the PageRank by just applying the PageRank function over the network I define. So yes, the graph I define. In this case, we should pay attention to the fact that this is a direct graph. So I define this not as a general graph. So these are not undirected edges, but these are directed edges. So from source to target. Is it clear for everyone how PageRank works? It's actually very, PageRank is very powerful as an algorithm. It's used not only on web search by Google and any other search engines, but it's used in many other cases, like in summarization. If we define a graph by having each node as, like each sentence as a node in the graph, and we can compute some sort of similarity, we can weight some edges, and we can then run PageRank to compute the most important sentences in the graph. And so to have to select only a subset of sentences. And we can run this, we can do this kind of operations also in other domains. So it's actually a general approach to compute the importance of a node in a given graph. Okay, if there is no question, I can pass to Elasticsearch. This is a more applied topic. So the idea is that we have an idea of how to build search engines, how we can actually build them. We can use Elasticsearch, that is a framework to create search engines. It's actually very, very fast. It's actually very fast. You cannot imagine. It's used for real-time searches. It's distributed. It means that if you have multiple servers and you want to run Elasticsearch in a distributed manner by exploiting the computation of different servers, you can do it. It's scalable, it's efficient, it's very, 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 very efficient framework to build search engines. Like some of the users, GitHub, Wikipedia, Stack Overflow, they are all using Elasticsearch in this case. Yeah. How is built inside? So Elasticsearch is a document-oriented database. It means that each document that is indexed in the in Elasticsearch is a document. I don't know if you are familiar with the NoSQL databases or like MongoDB and so on. So this is a similar to MongoDB, is a document-oriented database. So we have indexes in this case that are built, and they have they may contain heterogeneous field. It means that if I have a single element indexed in Elasticsearch, it's a document. It may contain different fields, like the text of the document, and then other elements, other information that can be actually different from one document to another. It uses a library called Lucene that is open source to index the documents. It has the RESTful API, so you can use this framework in different programming languages. And we have each document that is indexed in a specific index. It means that we can use, like having different tables, we can build different indices, but each document is stored in a single index. If we want to store a document in multiple indices, we should clone this document in both of them. So an index in this case is like a table. It's like a very big table that we can use to search for documents. This is some just the intuition of how it works. The idea is that I can run different kind of requests. So this is a post request. I want to store something, post. I want to store something where I can use the name of the index I'm creating, and I can use an ID to store my document. I can define an ID that is unique inside the index for my document. And then like a document is like a JSON file, like a JSON document. I can have query like key value dictionaries like text, and then I can have the text of the document, ID. In this case, is actually this one, ID, and they actually have the ID of the document. So I can actually define the document as a JSON document. Yes, here I have an example. I want to, yes, in this case, I use the put request to update a document. So I use the index name and the ID to identify my document. I use the update request to update the document, and I want to set the color equal to red in this document. If the color key exists, it will be changed the value to red. Otherwise, it will be inserted the color key with the value red. And if I want to delete a document, I can just use the delete request with the index name and the ID that identify my document and delete this. The idea is that documents are not mutable, are immutable. It means that once I run my update request, what happens is that I insert a new document with the same ID, and meanwhile, I delete the previous one. So I'm just re-indexing another document by using the same ID and deleting the old one. And the removal of document is not immediate. When I run the delete, it means that the document is not searchable anymore, but it's there, because the fact that that Elasticsearch is distributed, it means that it actually may take some time to delete all the copies of the document that I have distributed in different servers. Okay, the idea is that the score function, the scoring function, is the core of Elasticsearch. It means that what I want to do is to associate a score at each query that is inserted by the user. The score function is actually the core of the search engine, any search engine, but also in Elasticsearch. The standard scoring function is the FIDF or BM25. I think you have seen this with Professor Pagliero also in other courses. they use like the syntax of the document to match some words, and so to compute how relevant is a query to a document. It's semantic? No. It's fast to compute? Yes, but it can be modified. So we can actually define our personalized scoring function. During query time, if I retrieve a set of documents by Elasticsearch, what I have is a set of documents with a score field in the results, and like higher values for this score means that this document is more relevant to my query. So I have actually a descending order for the documents that I can use to rank my documents. If I want to do custom scoring, please refer to those slides when, like at the next lab, when we will create a search engine for Wikipedia. So the idea is that we can use, we can define our custom function score by using a JavaScript-like formula. And actually how the request is composed, we have a GET request, we have the search keyword, and what we do is to actually, we have a query, and we have a script score, or a script that actually computes the score. If we don't provide this script score, by default, it uses TF-IDF or BM25. It depends on the version of Elasticsearch you're running. Yes, another very important thing is that we actually have a specific field in the document for dense vectors. Why? Because semantic search is actually deployed in real life, and what we can do is to create a specific property in the document called, in this case, dense vector having a dimension of 768. That is actually the dimension of the vectors created by BERT. And so in this case, I can pre-compute the vector representations for my documents. I can then use them at query time to compute, the cosine similarity of the query with all the documents. Okay, yes, this is the library that is actually the official low-level library of Elasticsearch for Python. It was designed as a very lightweight wrapper around the Elasticsearch APIs, and is very easy to use. And it's actually, once you get how Elasticsearch works, it's actually translating this into Python, and it's actually very easy to use. Here I have an example. I think it can be useful for the lab. So I have the library imported. I create my Elasticsearch instance. I am creating a new index. In this case, I called it like DNLP. I have a document here. So this is my personal document. I'm not a PhD student anymore, but yes, I have my personal document. So name, surname, role, and bio. And I can just index this document by providing the index and the body of the document I want to index. Just a quick mention to another library that is Elastic Transformers. You won't use it in the lab if you don't want, but actually it's a binder that allows you to create and to define the input-output operations for creating dense vectors. It means that you can actually connect this library to a model. In this case, it's a sentence transformer model, and you can actually compute the vector representations of the documents to index them on Elasticsearch. In this case, yes, the sentence transformers are based on deep transformer-based models. So it's actually a quick mention for any of you that want to deep into the details of these libraries. Okay, here we have some references for the today's presentation. If I can if you want, I have two questions related to the IR word from the exams. If you want, we can discuss these questions, these exercises actually together in a few minutes. Do you have questions on the theoretical aspects, like on PageRank, link analysis, Elasticsearch? No questions? Okay, if you don't have any question, we can pass to actually two of the questions that were actually taken from previous exams. Those are the kind of questions, like the questions that we provide in the exam. One is this one. What of the following statement holds false for information retrieval systems? So which one is false? The A, in the binary model, queries are defined using Boolean expression. So please pay attention to the fact that we are false. So the first one is, in the binary model, queries are defined using Boolean expressions. The second one, like the B, is the dictionary of terms for the inverted index is built by defining the set of unique words in the corpus. Yeah, you have space. The C is, recall, is not used for evaluating IR systems. Vector space models represents both document and queries as vectors of weights. And the last one is TF-IDF can be used to obtain document querying matching score. Who votes for the A? Who votes for the B? Who votes for the C? Two people. Who votes for the D? Who votes for E? The last one. Okay, so the sum is not the sum of people here. But yeah, okay. The correct one was the C, because recall is not used for evaluating IR system. It's actually not true, because I said you that it's actually one of the most used evaluation metric for IR systems. Do you have a question on this? So in the binary model, queries are defined using Boolean expressions. This is actually what binary models do. The dictionary of terms for the inverted index is built by defining the set of unique words in the corpus. That's actually how the dictionary is created. So the number of the set of unique words in the corpus creates my dictionary. The C is false, so it's false, but it's the correct one. The D, vector space models represents both document and queries as vector of weights. Yes, that's actually how the vector space models are defined. We have queries and vectors that are embedded in the same embedding space, and we can actually then perform some similarity metrics. And then TF-IDF can be used to obtain document query matching score. Yes, this is one of the metrics that is one of the scoring functions that is used by default in some versions of Elasticsearch. Second exercise, then I will finish. So this one is considering the EATS algorithm during the hub update step. What happens? So the A, each node relevance is normalized by the number of nodes, n. Each link relevance is normalized by the number of nodes. Oh yeah, each link relevance score and node relevance score is normalized by the number of nodes n. The C, for each node, the hub score is the sum of the authority score of each node that it points to. Or for each node, the hub score is the sum of the hub scores of each node that points to it, or none of the above. Who vote for the first one? If you want to read, like, I'll give you like 10 seconds because I read it loudly, but you can actually reflect if you want. Okay, who is for the first one? A. Who is for B? Okay, who is for C? Who is for D? And who is for E? None of the above. No, nobody is not for none of the above. Okay, the correct one was the C. Why? because actually this is what the hub score, like hub update, is doing when doing like the update of the hub scores. The first two, why they are wrong? Because the relevance score, like each link relevance score is actually, we don't have the relevance score for a link. The first one is wrong because it's not normalized by the number of nodes. It's normalized by the sum of the hub or the authority scores, respectively. Then why this is wrong? Because for each node, the hub score is the sum of hub scores of each node that points to it. No, it's for the hub score is the sum of the authority score, and the authority score is the sum of the hub scores, and vice versa. Is it clear? Okay. So if it's clear, this concludes my yes question. No. Okay. They, of course, we will during the exam we'll ask question like more theoretical about the attention and so on. The idea is that you have a mixture of closed and open questions. So you have question like this where it's difficult to check. Yeah, we don't want you to do like raw mathematical computation. We don't need this. But it's like more on the concepts that we introduced during the course. Meanwhile, the second, like the open questions, we also ask you to provide some details, perhaps on the mathematical formulation, perhaps of the PageRank. We don't ask specifically to give us the formula of PageRank, but if we ask you to introduce PageRank, you can perhaps also provide the formula of the PageRank if you know this. Is this clear? Okay, if there is no question, I will finish the lesson for this part. You can have a break of 15 minutes, 10 minutes, and you can see each other with Professor Pagliero and after the break.
Okay, so I was saying that now we will complete the overview of recommender systems, and then at the end of the presentation, I will show you we will do some exercises on design of NLP pipelines. So let's start recalling the main distinction between recommender systems. So we can divide the recommender systems in three main categories. First of all, we have collaborative filtering systems, which focus on leveraging the similarities among users. So you recommend some items to a user because another user or other users who are similar to him will have already positively rated that items or that item category. Okay, this is the main idea of collaborative filtering. Of course, this approach implies that you are not considering actually the characteristics of the items you are recommending. Conversely, content-based recommenders focus on analyzing the item characteristics. For example, if you recommend a book, you try to infer the main topics covered by the book, the authorship, try to understand the competencies, the skills that are needed in order to understand the concepts explained in the book. So this kind of these pieces of information that are of course crucial to discriminate between recommendable and not recommendable items. Okay, if you and these systems work even in the absence of information about additional information about the users. So if you don't know anything about the user, you still are able to recommend something based on the content solely. Then there is the third category of items of recommender systems, which are called hybrid systems. We have already seen that there are some variants of hybrid systems, but basically they combine the properties of content-based and collaborative filtering systems. So you leverage both user information and item characteristics. When we design recommender systems, we have some challenges to overcome. The main challenges we have to address is the sparsity of the so-called utility metrics. What utility metrics is? Utility metrics is the metrics that collects all the previously assigned ratings to each user, for each user to any item in a collection of recommendable items. Of course, if you are a user, you can rate explicitly an item when you have, for example, purchased a book. You can, or you have you stayed at an hotel, or you went to a restaurant. You can rate and give your feedbacks, your preferences. By collecting the explicit feedbacks, or by extracting some implicit feedbacks, like, for example, the click rate or some other metrics, some other measurements related to the user activities, you can fill a matrix like this, which, like this, which is a user item matrix. And for each item, you have a score, a rate, that indicates the level of preference, the rating of the user for that particular item. For example, in this example, the ratings range between 1 and 5, where 1 means low rate and 5 means very high rate. So the problem, one of the main problems, is that, of course, given the entire population, the entire collection of items, which is potentially very large, this matrix is relatively sparse, because many of the user item combinations are missing, and that user has not rated that particular item yet. So it's a sparse matrix which is full of zeros or missing values. The other problem is that if you have new items which are added to the collection, because maybe a new model of mobile phone is now available in the market, okay, you don't know whether it could be recommended or not, and who are the potential users, because you don't have any history about the item. This is called first rater. The third problem is called the cold start, and it's the same problem, a similar problem, but from the user perspective. If you are a new user which is recorded in the system, as recently recorded in the system, maybe you created a new account and you registered to an e-commerce platform. Then we don't know anything about you. Maybe we can try to ask you to provide some personal information, like the age range, the provenance, or some keywords of interest. But at the end, you have limited information about this user, and this results in a difficulty in modeling the preferences of that new users. This is called cold start, because after a while, when you collect new information directly or indirectly, you will be definitely able to improve the quality of the recommendation, because you can personalize the recommender system offer. Then you have some problems also related to content-based filtering, because if you filter the content based on their properties, the system tends to specialize, to put an overemphasis to some characteristics of the items that are strictly related to some key properties, then if you recommend something to a user, the so-called firstly evaluated items, firstly recommended items, then the system tends to create a sort of bubble where all the items that are recommended to that user are all similar to some extent, because you have no sufficient variance in the properties of the recommended user. This is a common issue in a recommender system because it is related to the problem called the feature called the serendipity, because your system, if your system tends to offer always the same properties, the same kinds of items, the system this results in something that is repetitive, boring, not interesting at all. So you need something that is interesting, relevant to your purposes, but also new, something that is unusual, unexpected. So some surprising properties. Okay, and this is called serendipity. Of course, the popularity of the recommended items is very unbalanced. So the distribution is skewed because you have a few items that are most very popular, highly popular, and you have many interactions, many user preferences, and many feedbacks. And there are plenty of other items that have low rates, even because most of the users ignore them or have provided only just very few rates. So this is called a long tail phenomenon. So the item popularity is very variable. Okay, when we try to model the problem in a content-based scenario, you have to define the item profile for each candidate item. So given a user, you have to pick the top K highly ranked items by matching the item profile with the highly rated ones. So the idea is to try to compute similarities between items and try to recommend the most similar candidate items. So if you are, I want to show you a picture here. Let me take the picture here. So if you are interested in horror movies, I have to look into the candidate items consisting of other movies, try to understand which category they belong to, and of course the more similar they are, the more better they are as candidate items to recommend. Because of course I try to infer what is the preference of the user based on the item content solely. So you don't know anything about the user, but you try to capture the item-based information. And of course, in order to compute the item similarities, we can leverage the measures you already used for evaluating vector text similarities. For example, when copying with textual metadata or textual contents. For example, we can leverage cosine similarity or Euclidean distance, where in case the content or the description of the items can be modeled as vector embeddings. There are also some more straightforward, more traditional systems that compare items based on their syntactical properties. So, for example, you can compute the TF-IDF of the words in the documents, and you compare two documents, how much these two documents are similar based on the TF-IDF metrics. We already know very well because we have mentioned this very many times. Okay, so for the collaborative filtering system, we have two main approaches. One is called memory-based and tries to leverage the ratings in the utility matrix. So what a user has previously rated, positively or negative, in order to compute the user item match, to estimate the user item match. So if you are a user, if you have some characteristics, I already know some the characteristics of other users. I look for users that are similar to you, and based on the preferences of that similar users, I try to infer the preferences, the rates of your rates to some candidate items. So what you would rate for an item that is you have never seen, you have never purchased, but only because you are similar to another guy, and that guy is very similar to you, so it is likely to have similar preferences. This is, of course, just an assumption, so it's not necessarily true, because if we are very similar, maybe we have different interests, but the idea is that if you come from the same region, you have the same age range, you have the same habits, and potentially we are interested in purchasing, for example, or the same books or watching the same films. And then there is another kind of collaborative filtering models called model-based, which try to estimate the rating, the rating of a user to a particular item using some machine learning models. So you build a model that estimates the missing values in the utility matrix. So if you have the matrix, of course, it is sparse because some of the pairs item user are missing. You try to infer that values in order to, of course, try to maximize, to look for the items that maximize the user similarity, the user preferences. The higher the rate, the better the better the candidate is. You can assign to the target item a rate. This is similar to those assigned to the most similar items, to the most similar users. This is this approach that I have already explained to you before is also called the user-based approach. But you can also try to assign that the target item a rate that is similar to those assigned to other users to most similar items. So you can try to estimate the preferences of the target user in different ways, and this is shown in this picture. So you consider the similarity between these two users, and then you estimate, you can derive, for example, the preferences to some movies that you know that the similar user has already watched and is positively rated. Or you can look at the item level similarities and try to infer, see if the user A has rated movie B, movie 2, and I'm another user who has I'm looking at I would like to watch movie 6, and then these two movies are similar, then I can recommend to him to user B movie 2 because of the similarity between movie 2 and movie 6. So the driver here is the similarity between the items instead of the similarity between the users. So here is the formulation where the function here is the set of k users that are most similar to the target users who have already rated a particular item called I. This is the user-based scenario. Then you have the item-based scenario where you find the items that are most similar to the target item by estimating the rating based on the rating of 4 given to other similar items. And here is the formulation. So it's simply a weighted average computed over the similarity matrix. And these are the ratings explicitly given by the user or implicitly given by the user. So in order to model, to apply, to estimate the missing values in the utility matrix, you can apply many different approaches. So you in the literature, in the scientific literature, you find plenty of different strategies ranging between traditional reduction systems, probability models, machine learning techniques. So there's almost everything. The point is that you want to estimate with a good level of accuracy the values that are missing in the utility matrix. So, for example, you can simplify the problem trying to decompose the matrix in order to capture the most relevant, the most significant aspects. The singular value decomposition is instrumental for simplifying the task, and it is the same already explained for topic modeling. So it's the same formula. The idea is to reduce the utility matrix to a simplified reduced version with a lower rank, and this of course allows us to derive the singular values and the singular vectors, the eigenvectors of our matrix. So you basically find the main components, the most representative features underlying hidden in the utility matrix. So you pick a user rating matrix, user item matrix, which contains the ratings. You transform using the matrix factorization, the SVD matrix factorization, in a product of a user concept matrix multiplied by a singular value matrix, which is a matrix which is diagonal matrix, where the singular values are in the main diagonal and the other values are all zero. And then you have the item concepts. So based on this representation, you can compute, similar to topic modeling, what are the concepts that are mainly describe items or users. So you can do some reasoning of what are the preferences of the users or what are the characteristics of the items. Of course, this approach relies on the assumption that the description of the items and description of the users is inherently redundant, because most of the information contained in this matrix is partly redundant. So there are many overlaps. There are many obvious correlations. So what you are really interested in is not to find obvious correlations, which are, of course, simple but not very useful in terms of recommendation. What you are looking for is to find some hidden yet interesting yet relevant correlations among users and items. So you can apply the singular value decomposition in order to have also visualization, which is particularly effective because you can associate, for example, here pairs of similar users or pairs of similar items, and in the space you can also compute the distance between the users and the items, because they are all represented in the same space. Okay. Probabilistic approaches try to maximize, again, the likelihood of giving a high rate to a given item by a given user. So these are typically estimated using Bayesian probability functions. It is a common way to solve the problem is to apply probabilistic models in order to estimate the probability for a given user to choose to positively rate a given item. And then, of course, the idea is to recommend the items that maximize the posteriori probability. And then there are more complex models relying on graph structures. And here the idea is to visit a graph, which is a user item graph, which connects both users and items. An item is connected to an item is connected to a user if you have a rating, and you can also extract some random work, do some random works on the graphs in order to extract some so-called graph embeddings. These are representations of the text of the graph are similar to the representation of the text. So similar to text, when you have a long piece of text, you can scan or slice over the text with a context window and try to derive a word level embedding. Here you do some random walks on the graphs in order to derive the embedding, so vector representation of each node. This is the idea. And given the vector representation of the nodes, you are capable of comparing, for example, users and quantify the similarity among users, or quantify the relevance of an item for a given user. So this is the main idea. This is quite a quite recent approach and quite effective. You can also apply a similar approach, representing the users and the items in the common space, and apply clustering techniques in order to group similar items of similar users. So the idea is to clearly separate what are the clusters of users that behave similarly for example, designing a collaborative filtering approach. And finally, yet another approach is to try to extract, given a list of previously recommended items, the associations among these items. For example, if I recommend A and B, then I recommend C, and these associations can be exploited to do additional tag recommendation. So if you are, for example, a social user, if you use a social platform for annotating, for example, for uploading, sharing, and annotating photos, okay, a user may partially annotate a photo with some tags or some keywords. I can collect the previously assigned keywords, analyze the correlation with, for example, association with mining techniques, and I see that some of the keywords are frequently occurring in the annotation dataset. These implications, these associations among keywords can lead us to suggest additional annotations to partly annotated photos. So if you have photos with few annotations, you can recommend automatically additional keywords that the users have not assigned yet. Okay, so this is something like I suggest you to assign the next tag to assign to annotate a photo. And the same approaches are also applied in other contexts, like, for example, recommending locations instead of photos or keywords or images. So you can analyze the geographical map and recommend, for example, the locations or the points of interest that the user, a tourist, should visit, and this works in the same manner. So the idea is again the same, to cluster and correlate users, groups of users, locations, or groups of locations. Or here, of course, you have to take the geographical distance into account, because, of course, if you are here and you are more interested in getting recommendations about nearby locations, not for example, recommending this. Maybe this is a very relevant item to recommend, but it is not reaching that point is not affordable in a reasonable time. Okay, let's focus on text-based recommendations that are systems that of course are capable of leveraging contextualized embeddings like BERT in order to do recommendations. Here is an example. This example is called RecoBERT, which is an abbreviation of recommender based on BERT. And the idea is very simple. You have items which have descriptions, metadata descriptions consisting of titles and descriptions and categories. And you learn some catalog, you learn a language model on top of this data, which allows you to describe, to model the similarities among the items in terms of content of the related associated metadata. Okay, so here you don't, the idea is not to go deep into the full text, because these items can be also not text, maybe images or videos, but try to get the similarities among metadata if you don't have, if you have enough metadata. Typically, when you annotate some resources, it's quite common to have a short title and the description, and the size of that piece of text is commonly shorter than 500 tokens. So it's you can apply BERT and generate a unique vector embedding, so an encoded version. And this encoded version can be exploited in order to generate the recommendations. So you get title description pairs. In order to train the language model in a self-supervised manner, you have to generate both positive and negative pairs. The positive ones are the mappings between title and description, like in the question answering scenario. I pick the text of the question and I map it to the corresponding to the text of the correct answer to that question. And this is the positive example. Then you have a negative example, which consists of another question associated with a random answer not corresponding to that question. This is the negative example. Here in the example, we have the title, like the question, and you have the description, which can be the corresponding description in the positive case, or the negative one in the wrong one, or a random one in the negative case. So in the training process, try to build a so-called topic description, title description model, which tries to leverage the similarities between title and description in order to understand what are the key properties behind the text, the content of the item metadata. And then this is the language model, the pre-trained language model, which helps you to give scores to the items according to the inference process. So you build a learning phase, which needs, of course, annotated data. The annotations are instrumental for extracting some relevant scores. And of course, if you are interested in, you can read through the publication, which is relatively recent. There are also item-based solutions which rely on BERT and contextualized embeddings. So not simply look at the metadata, but also look at the entire content. And you can also compare the items in terms of in terms of full text content, and of course you need to split the content of the text into parts, because the entire full text often does not fit into the maximum size of the maximum token size, which is 512. Or you need to leverage some more advanced, more more powerful architectures like long-form or similar, which are capable of extending towards hundreds of tokens. Okay, if you here is you can find other examples of BERT recommenders. The idea is pretty the same. Now I want to focus the attention on the evaluation of the recommender system. So once you have designed your own recommender system, or you have tried to run an existing one, you have the need of evaluating the quality of your system. So you have to quantify the performance of the system, and the performance can be assessed in different ways and according to different metrics. So you need to, of course, verify whether the recommendations were correct based on the expectation of the user. You need to then verify whether the recommendations are sufficiently diversified, or they cover maybe different categories or aspects. So if you have a profile of a user who is interested in many different aspects, I want to diversify and provide the diversified recommendations, like, okay, you are a user who likes, for example, sport, but I know that your preferred sport is basket, but maybe I can also send you some movies or some invitations about other sports like soccer or cricket or whatever. So you can try to get diversified solutions, recommendations, in order to improve the serendipity of the system. So there are some metrics that allow you to evaluate the performances. Here you can find some examples of benchmark data, ranging from reviews of Amazon users, reviews of products, of purchased products, reviews of books, recommendations for books, recommendations for songs, recommendations for movies. So they mostly include textual annotations. For example, if I have a review, I can also analyze the text of the review to understand the motivations behind the recommendation. Or even the content of the item can be textual in the case of books, for example. In case of audio, speech, or videos, you can also apply NLP solutions on the transcripted version. So you generate the transcripted of the audio speech, and then you apply some language models or similar. So here you can find some characteristics. Why do we need benchmark data? Because the idea is to compare the performance of the systems on some data sets that are publicly available, on which many existing models have been already proposed. So you know what are the state-of-the-art performances. If your system is capable of achieving comparable performance or even higher, okay, then you can consider your system as a good candidate solution. Otherwise, if your performances are order of magnitude lower than the state of the art, probably your solution is not the best one. And so you have an idea to benchmark your solution. How to evaluate the quality of the system? So, for example, if you have the utility matrix with some empty cells, you can try to predict the missing rating values and compute the error, which can be computed as a root mean square error of the predicted values. So the predicted with respect compared to the actual, the expected one. Of course, in order to do this, you need a test set where a test utility matrix where the missing values are actually not missing. So you already know the rate, but you hide that information because you want to test your system and try to let the system guess the actual value of the rate and see what is the error in the prediction. This is typically, since rates are typically numbers or stars, or for example categories from 1 to 5 or 1 to 3 or from 1 to 10, so this is typically modeled as a regression problem, because the ratings are often ordered, so like one from the lowest to the highest, and of course if your system is not precise enough, then you cannot choose whether to assign 4 stars or 5 stars. Okay, but it could be slight imprecision. Whereas if your system fails and assigns a rate of 1 instead of 5, this is a big error, a big issue. Okay, so it's not simply correct or not correct. It's not binary choice. It's most cases it is more appropriate to choose to adopt to model the problem as a regression task. Then your recommendation system typically produces a ranked list of recommendations. Typically, you have a target user. I have a collection of candidate items which are potentially recommendable. I have to pick the top K best K items from the collection, and I have to provide a rank, to produce a rank, which is similar to the case of information retrieval that I have described you next the previous lecture. So I have to return a rank of shortlisted items. So in order to evaluate the performance, I can also apply some information retrieval metrics like precision at K or recall at K. For example, the precision at K indicates the percentage of correct items in the top K, where K is a parameter, typically is user provided. So you set a fixed number of K, and you compute the percentage of correct items, because you already have in your ground truth a list of K actually recommended items. So the items that the user is really interested in. K items, you try to match that K items with the K recommended ones. Then you can also compute the correlation between the predicted and actual ratings. You have the possibility also to compute the mean reciprocal error, like this, which is the maximum of the over the item of the relevant items of the ranking. So you try to maximize the rank, or the coverage, which means that which is the number of items of users for which the recommendations have made prediction. So there are many different kinds of evaluation metrics, which are mostly derived from information retrieval. So it's nothing new about this topic, because it's a particular application of information retrieval. The diversity has the goal of increase the user satisfaction by mitigating the problem of overfitting. In this case, we talk about overfitting in the sense that we would like to avoid keep recommending the same thing or keep doing the same errors. So indeed, the model needs to be adaptive and to capture also different aspects, complementary aspects, or if the system is able to get some relevance feedback, you can exploit to leverage the user feedback and adapt the next recommendations to the domain or to the user preferences. Another very interesting field is called contextualization. So you can, and this is basically a field of multimodal learning, where you not only consider textual content, but also some multimedia content like books or images or videos or whatever, or podcast. You can, of course, try to derive some associations and correlations between items of different modalities. For example, a book written by a famous football player and a video of a football match. Of course, these two items belong to different modalities, so have different characteristics, but they belong to the same context. So if you are able to capture this context-aware relations, you can improve the recommendations in a multimedia and multi-domain, multimodal context. And you have also the chance to try to leverage the systems that were trained on a particular domain, and to bring that system, to transfer that systems on similar domains. This is called transfer learning. And the idea here is to try to reproduce, to exploit what is already known about a particular subset of items, which are likely similar to those in the target domain, not exactly the same. So of course, you would expect a drop in performances because you are not working in the same domain as the original data, as considering the original training phase, but you expect that the shift in the domain is not is partly beneficial, so you can keep training the model on an auxiliary domain and apply it to the target domain. Mainly because you have, for example, you have annotations, you have data, you have the ratings for that auxiliary domain. You can also purchase some annotated data, because annotations are potentially exploitable in order to collect new customers, to improve the revenues, to improve the user interest. So in this case, your goal is to reuse some information that is coming from another domain, which is typically data-rich domain, and reuse it in a data-poor domain, in a domain where there is typically a lack of data, lack of annotations. Even for issues related to privacy, related to, for example, the kind of users which are not familiar with IT technologies, so we are not used to rate something, to provide feedbacks. So there are plenty of cases in which this assumption holds. Okay, here the scenario is similar to before. You can, of course, especially in the item-based recommendation, in the content-based recommendation, you can, of course, leverage information from other contents, not only text, and have a mix of the two systems. Okay, the challenges I would like to mention are also related to privacy, because in many cases the user preferences, what the user is doing on the web, or what they're using as chosen as user preference, personal preferences, is protected by GDPR. So you have to pay particular attention to the data protection aspects, which are commonly managed in large companies by a data protection officer. So a DPO who is in charge, or is typically a legal man who is in charge of verifying that your applications are correct, are not respect the law and are in respect of law and the rights of each individual, because in this case you are deeply analyzing the user preferences, the user habits, and you are also making some decisions based on some potentially sensitive aspects of a human, like for example the race or the sexual preferences or whatever. So we have to pay particular attention to these aspects, which are commonly crucial in these recommended systems. So there are also some potential risk of bias in the model inference process. Okay, let's try to get an example of pipeline. I would like to start today, and then we will complete this exercise next lecture. So the idea is to have some examples of exercises which implies not simply to answer to a question from a theoretical question, but to think about a practical solution to a real problem, a real case. So basically, in the written exam, I will provide you also with some simulations, some examples of past exams. The questions are of three main types. Some closed questions. Closed, you have to choose the right one among 1, 2, 3, 5 questions, as Moreno has already shown you some few examples about this. And this is typically a theoretical question. Choose that. Or there are more theoretical questions, but open questions. So you have to write your own the answer, like, okay, please explain the characteristics of word2vec, or explain the differences between the word2vec and the fast text. Try to enumerate the pros and the cons between of the two. So, for example, you have to elaborate on how word2vec works, what is the idea, the distributional hypothesis, the neural network that is trained over a large corpus of data with the fixed size window, and that's it. So this is a theoretical question because you have to show your knowledge, your prior knowledge on this topic, and you have to, of course, have a clear idea of differences, pros, cons, but it's not a practical application. One question, typically the last question, is more practical in the sense that we formulate a practical case, very short, a few lines, and you have to comment, to elaborate on what is a possible solution to that problem. For example, an author wants to, and this is of course a very simple case because it's the first one we see, but then we will see other examples, other more elaborated examples. An author chain wants to analyze 10,000 reviews submitted to the author guest by the author guest. The reviews were submitted through a HTML form. Of course, you don't know a priori what was the language because the customers can come from the different countries, so maybe they wrote their reviews in different languages. And you have to enumerate the steps needed to build a sentiment analysis tool, which sentiment analysis means you want to predict whether your system your review is positive or negative. We have not analyzed how advanced deep solutions for sentiment analysis work. We will do it in the next lecture, but now we are simply trying to model the problem, which is a classification problem, a text classification problem, using an SVM classifier applying to TF-IDF representation of the text. So motivate the adoption of each step. So try to think about, okay, what should I do? Given that problem, given that data, I have a goal, which is specified in the question. What are the steps that I have to apply? What is the pipeline? What we call pipeline is a sequence of operations. Of course, it's a high-level description because you don't have to implement something. The implementation part will be related to the project, so it's not in the written part, of course, in the written test. I would like to ask you to reason about the possible solution and to explain how would you solve the problem, at least from a enumeration of points or steps, motivated. So you say, I do this, why? I do this, maybe using this or using that solution. I show you an example. So if you have to design a sentiment analysis tool, given a collection of raw textual reviews, so the first step is to clean the data, of course, because the data may include whatever kind of textual content, even some non-textual content or special charters. So you have to clean the data, remove some unexpected, not recognizable items. Then you have to detect the language, so to do language identifications. There are tools that allow you to simply detect what is the most likely language of a piece of text. They have, of course, some probability of error, but it's typically small if you have if you get a sufficiently large so a review, a complete review, not simply a few words. And then you can translate the text in order to get a uniform set of reviews, because of course if you have a mix of English, French, Arabic reviews, it's not possible to train a unified model. So you have to make the language of the text uniform using machine translation. Then we can apply the preprocessing step you have seen at the beginning of this course. So in order to design an SVM classifier, to train an SVM classifier, the classifier is typically as requested in the question. The classifier needs to be trained on a TF-IDF matrix. So this means that you have to clean the data and prepare the data in order to make it suitable for training the SVM. So what is the first step? The first step is to split the text into tokens, typically words in the simplest case. So you can apply word tokenization. The word tokenizer are available in most NLP libraries. You have seen Spacey. And the word tokenization consists in picking a raw piece of text and getting the list of tokens. Each token corresponds to a different word. You can also use some more advanced solutions which get also multi-word forms, like for example deep learning is a multi-word form, or machine learning. Then you can remove some stop words to counteract the negative effects of cursor dimensionality, in order to have to avoid having a so large training set with too many dimensions. We can remove those words that have little semantic meaning, like for example conjunctions, prepositions, articles. This step is called stop word elimination. So you are after getting the word tokens, you can remove some of them in order to simplify the representation, to clean the representation. You can also apply stemming or lemmatization if the language if it can be applicable, because of course stemming and stop word stemming is not always available for all the possible languages. It is available for most spoken languages, but there are some languages for which you have a few linguistic models, so you don't have the chance to do this. And after this, you can compute the matrix of TF-IDF. So typically in the solution, you can just write down the formula. Okay, I use this formula to compute the value in the matrix. We have seen this few slides ago. So this. In the presentation of recommended system, you build the concurrence-based relational representation, where each line, each row in the dataset corresponds to a different review, whereas each column corresponds to different word. and the value corresponding to a given pair of row and column is the TF-IDF value associated to that word in that particular review. Okay. Of course, you also need one extra column corresponding to the class label. The class label, in this case, since we are addressing a sentiment analysis problem, the class label will be positive or negative, okay? Or of course, it depends on the kind of annotations you have. Like, for example, positive, neutral, or negative. It depends on the kind of examples or annotations you have. And you can also try to explore the correlations among the word, between the words and the target. For example, if there are words that are more discriminating in choosing the right class. For example, wonderful or awful or sweet or fantastic. These are words that have that convey a strong sentiment feeling. So it's very likely that they are correlated with the target. So it's better to focus the attention of the machine learning model of the SVM on that words rather than others. So you can filter out some irrelevant features using feature selection step. Of course, if you want, you can also provide some examples of which feature selection model you can apply. There are plenty of solutions which are not which are covered by other courses like a data science course. You can mention some examples if you want. Then you split the data. You have the examples of labeled data in train, validation, and test. You try to train the model on the training data, evaluate the model on the validation set in order to identify the most appropriate hyperparameters of the system, and finally test it to assess the performance of the system on the test set. The validation part is, as you know from the courses of fundamentals of machine learning, is mainly focused on finding the best configuration of the system, which of course depends on the analyzed data distribution. For example, you can decide which is the best kernel, the best number of the best parameters of the classifier. So it's the idea is to find a configuration that is appropriate and sufficiently general enough in order to effectively classify the test samples. You can, of course, if you have enough data, you can also design some, do it in a cross-validation phase, so generating multiple times the train and test sets. Of course, in this case, you don't have so much examples to do this, and it is quite uncommon when you have to train a deep model, because training a deep model is very computationally expensive. So if you have to redo the training phase many times, it's very, very labor intensive. So I take only just a couple of minutes more, because I want to show you the differences between the example one described here, which entails training an SVM classifier based on TF-IDF representation, and a similar problem, but in this case, we want to train a sentiment analysis classifier based on a BERT model. Okay? Now, the problem is the same. The solution is different because you rely on BERT instead of a simple SVM classifier. Okay, now the idea is to use the BERT capability of modeling data and addressing classification. So here is an enumeration of the steps required to use BERT. I want to show you the differences. I will recall this next lecture, but let me just briefly highlight you the key points. So first of all, you don't need stop word elimination, stemming, lemmatization, because BERT is capable of getting the key properties in the sequence based on attention mechanism without explicit manual cleaning of the text. You do need tokenization as well, because of course BERT needs a separation of the text into tokens. BERT has the constraint of handling sequences of no more than 512 tokens. So if you have longer pieces of text, longer reviews, you need to split the text into parts and process each part separately. You can apply, you have two options. You can detect the language and use a monolingual BERT, like BERT on English, BERT on Italian, BERT on French. There are some you can find on Hugging Face or similar libraries. There are releases of BERT pre-trained on different languages, and you have to find a pre-trained version of the model on that language. Or you can use some multilingual version of BERT, which are already trained for and work on most spoken languages. Here is the link, so you can take a look to the model. It's a very huge model, so it's not easy to retrain it from scratch. Don't do this because it's very, very complex. After finding the pre-trained model, you have to specialize it for the given task, and the task is sentiment analysis, which is a particular case of classification. And given a review, you have to assign the class which corresponds to the sentiment score, and you have to fine-tune the model, okay, for the particular task. So the second part of the BERT training, which is pre-training and fine-tuning. So you have to decide the task and fine-tune BERT for the sentiment task, and finally you test it. Okay. So of course, given the limited number of samples of reviews, you are not capable of retraining, pre-training the model from scratch. So of course, it's impossible. But you can start from a pre-trained version and fine-tune, leveraging the annotated data. Okay, please. Yeah, this BERT, the fine-tuned BERT version is the classifier. No, okay, you can, there are two options. You can, if you can use a BERT representation embedding, which means that you have, you get simply the vectors, the numbers corresponding to the sentences. These are the vectors of the corresponding to, this is a review, this is the vector, this is the review, this is the vector. And then you can apply a classifier here like SVM on the generated representation. But this is the pre-trained representation. If you, sorry, this is a representation that should be tailored to your data. If you have not enough data, it's better to take a pre-trained version and apply the fine-tuning stage, which replace the use of a specific classifier because it's already tailored to the classification task you need. So you have to address this problem only if the fine-tuning stage is not defined for BERT. BERT already provides you some solutions for specific tasks like question answering, classification, sentence pair similarity. In that cases, you can simply neglect the choice of a new classifier and rely on the fine-tuning stage. So use BERT end-to-end. So an end-to-end solutions with BERT. It's not mandatory, but typically it's better because you are able to achieve better performances. because this representation is more, the pre-trained version is more general, more robust to, and avoids doing overfitting. Okay, I'm sorry because I'm a little bit late because we started a little, we took a slightly longer break. Next time I will complete the examples. I provide you some more examples of NLP pipelines, and then we will move to the next application, which will be entity recognition. Have a nice weekend.